Today, we're finding the widest vertical area between any 2 points that contains no other points. How would you approach this challenge given a set of 2-dimensional coordinates? Given an array of points, where each point is represented by its x and y coordinates, our goal is to determine the maximum width of a vertical strip such that no points lie inside this strip. The strip sides must be defined by the x-coordinates of 2 existing points, and its height is infinite. Note that points on the boundary of the strip are allowed. A naive approach would be to iterate through all possible pairs of points to define the left and right boundaries of a potential vertical area. For each pair, we then iterate through all other points to check if any fall strictly within this vertical strip. If no points are found inside, we calculate its width and update our maximum. This involves 3 nested loops, leading to an inefficient cubic time complexity. The space complexity would be constant, as we're only using a few variables. The key insight here is that the y-coordinates are completely irrelevant. A vertical area is defined purely by its x-coordinates. To find the widest empty area, we only need to consider the gaps between adjacent x-coordinates after they've been sorted. Think about it. If there's a wider gap between non-adjacent x-coordinates, there must be points in between them, making that area not empty. So we extract all x-coordinates into a new array. Then we sort this array. Once sorted, we iterate through the sorted x-coordinates, calculating the difference between each adjacent pair. The maximum of these differences will be our answer. We initialize a variable to track the maximum width and update it during this final pass. Let's trace this with an example, points 87, 99, 74, and 97. First, we extract only the x-coordinates, 8, 9, 7, 9. Next, we sort these x-coordinates, resulting in 7, 8, 9, 9. Now we iterate through this sorted list to find the maximum difference between adjacent elements. The first difference is 8 minus 7, which is 1. Our maximum width is now 1. The next difference is 9 minus 8, also 1. The maximum width remains 1. Finally, 9 minus 9 is 0. Our maximum width remains 1. No other adjacent pairs exist, so we're done. The final maximum width found is 1. This is correct because the widest empty vertical area is between x-coordinates 7 and 8, or 8 and 9, both having a width of 1. You'll spot this pattern when a problem asks for maximum or minimum differences between elements, and the order of elements isn't strictly defined by their input position, or when one dimension of multidimensional data is irrelevant. Sorting often simplifies problems by bringing related elements together. The time complexity is dominated by the sorting step, making it O of n log n. Space complexity is O of n for storing the x-coordinates. This sorting trick is a fundamental pattern. Try the next problem involving coordinate geometry and see if sorting helps. Don't forget to like and subscribe for more DSA insights.